Hello, this is Dr. Hanaa Assil, and this is part 2 of the questions and answers on electrochemical cells. An excess of zinc powder was added to an acidic solution containing VO2 with 1 positives and warmed gently. When the reaction is complete, a mauve solution had formed. Use the data given in the table to determine the vanadium species present in the solution at the end of this reaction. Basically, we're starting with VO2 with 1 positives, and we're saying we have excess of zinc, so we want to reduce it as far as we can. State the oxidation number of vanadium in this species. Write the half equation for its formation from VO2 with 1 positives. Okay, this is the table that we had, and we want to start with VO2 plus. So where is VO2 plus? That is the equation that says VO2 plus plus 2H plus to give VO, 2 positives plus water. The zinc is the reducing agent, so the zinc will have its equation inverted. Okay, can we go any further? VO2 plus, we said we have excess of zinc powder. Then we try to go further, so that would be the VO. Please note where are the positives, because that could confuse you. So the VO, 2 positives plus 2H plus to give V3 plus. Now, can we go any further? We have V3 plus going to V2 positives. All of these are below zinc. So the zinc will reduce all of these species. Now he's saying state the oxidation number of vanadium in the final species. Of course, we have V2 plus, and we want the overall half equation. We said if we have any species before and after the arrow, we cancel. So these are the species that we cancel. We add up whatever is left. So this is what we have. Can you see that? And he wants the oxidation number in the final species. Of course, we were able to reduce it to plus 2. That is the lowest oxidation number for vanadium. Are we okay? Okay. While still warm, the mauve solution was filtered into a boiling tube to remove the excess zinc. Now, during filtration, the solution became green. That means something happened. On standing for some time, the solution finally turned blue. These colors would be an indication when you study the chapter on transition metals. The transition metals will tell you the indication of these colors. But for here, we don't need to know the indication of these colors. We just need to look at the table. So we're saying that we ended up with V2 plus. Now, during filtration, it is changing. So that means the V2 plus must be oxidized. It cannot be further reduced. So it's obviously being oxidized. Now, it's being oxidized by what? Well, we have oxygen in the air. So as I'm filtering it, the solution is hot while still warm. So there will be a reaction between the V2 plus and oxygen. So it will be oxidized. And that is why the solution becomes green, and then on standing it becomes blue, showing the presence of VO2 positives. Explain the changes of color. Of course, if you look at these equations, then this means that the V2 plus was oxidized by oxygen in the air, and then it became V3 plus, and this is the equation. Calculate the relevant E cell. Well, to calculate it, we add up the half equations, and this is the final half equation. The E cell for each of these, if I'm going from V2 plus to V3 plus, then I am inverting the sign in the table. Oxygen going to water, I wrote it as it is, and then I add them all up. The E cell for that V2 plus to V3 plus is this total E cell. Then we said it continued to be oxidized. So it continued to be oxidized to oxidation state +4. I look at the equation in the table. So this is V3 plus to VO2 positives. So that is the inverse of that equation. With oxygens, again, we said in order to add them all up, we need to make the electrons the same by multiplying through. That equation originally had 1 electron, and the oxygen has 4, so I needed to multiply all through by 4. And then we cancel whatever is before and after the arrow. Again, I'm going to remind you, if I have water before the arrow and water after the arrow, I cancel and I write what is left. I have H plus after the arrow and H plus before the arrow, I cancel and write what is left. And of course the electrons are cancelled, and I write the resulting equation. So this is my resulting equation. Now the E of that, we inverted the first one, so we inverted the sign. So now it is minus 0.34 plus 1.23. So the E cell is plus 0.89. Please make sure you provide all the information required. So he's saying write the equations. So we wrote the equations and calculate the E cells for each of them. Suggest why the solution containing blue VO2 positive ions might be expected to change to yellow VO2 with 1 positive, but does not do. That reaction does not happen. Again, we look at the data and we look at these two equations. What are we talking about? We're talking about VO2, VO with 2 positives. It would be expected to change to VO2 with 1 positive, so that is that equation, but it does not do so. Remember that if we write the E cell for this would be the plus 1.23 minus 1, because we are inverting that equation. We're starting from VO with 2 positives, changing it to VO2 with 1 positive. So you invert the sign. And this E cell total is plus 0.23. This is regarded as a small number, but it is positive, so it should be feasible. So it would be expected to happen. But if he says that it does not happen, then that means the activation energy is too large. Remember, if the E cell is positive, it should be feasible. If it does not actually occur, that means the activation energy was too large. A cell could be set up as shown to measure the electrode potential for the reaction between iron 3 sulfate and chromium 2 sulfate. This reaction is classified as a redox because the chromium 2 ions are what? We're starting with chromium 2, ending up with chromium 3. So what happened to the chromium? Of course, it is oxidized, increase in oxidation number or loss of electrons. So it was oxidized. And that means the other species, the iron 3, was acting as what? As an oxidizing agent. Correct? Okay. The reaction proceeds spontaneously. So we are saying the reaction is feasible. What does that tell you? We said the reaction is spontaneous if what? The E cell is positive. And we said if the E cell is positive, that means the delta S total is also positive. So this is the correct choice. Which of these saturated solutions should be used in the salt bridge? Remember, we said the salt bridge is an inverted U-tube that connects the solutions of both beakers. and it is usually a saturated solution of which of these? Of potassium nitrate. Remember that the others would either react or it would form a precipitate, and that is not a good choice. So the other ions in this case would react. What mass of iron 3 sulfate is present in 100 centimeter cubed of solution used to measure the standard electrode potential of the cell? To measure the standard electrode potential of the cell, I need the iron 3 concentration to be 1 mole per decimeter cube. So that's what we're trying to get. Now, in order to make 100 centimeter cubed of the solution in the beaker, and remember that the solution in the beaker is made up of iron 2 and iron 3. I want the iron 3 alone to be 1 mole per decimeter cubed in that solution. So, you should remember, iron 3 sulfate, 1 mole of iron 3 sulfate makes 2 moles of iron 3 plus. Remember that the concentration we're talking about is 1 mole per decimeter cubed of the iron 3 plus ions in the total solution. But any mass of iron 2 sulfate, 1 mole would give 2 moles of iron 3 plus, and that means the number of moles of the iron 3 plus, I want it to be 1 mole per decimeter cubed. So I want the concentration is 1 and the volume that we have is 100 centimeter cube. That means 0.1 decimeter cube. So I want the number of moles of iron 3 to be 0.1. But then that means I need half that number of moles for the iron 3 sulfate solid, because each mole of iron 3 sulfate makes 2 moles of iron 3 plus. So if I want, and that is what we want in the final solution, we want 1 mole per decimeter cube. And that means the number of moles of the iron 3 plus in the 100 centimeter cube should be 0.1 mole. That means the number of moles of the sulfate solid should be 0.05. Get the mass of that, and the mass of that is number of moles times mR, and that gives you the mass of 19.995. Are we following? Please remember, if we have 100 centimeter cubed of the solution, I need the concentration of each of the ions to be 1 mole per decimeter cubed. Now, the iron 2 sulfate produces only 1 mole. So the number of moles of the iron 2 ions would be the same as the number of moles of the iron 2 sulfate. But here we're talking about iron 3 sulfate, and you should remember that 1 mole of iron 3 sulfate will actually form 2 moles of iron 3 plus ions. And that means the number of moles of the Fe2SO4 this should be half of what we want, and this should be the mass that we get. The reaction between iron 2 and manganate ions is shown. Solution A contains iron 2 and iron 3. Identify the substances used for the electrodes. Again, what do I have in X? Where is X? X is the solution A, is the electrode in solution A. He's saying that solution A is iron 2 and iron 3, and we said if we have a mixture of ions, no solids, then the electrode should be platinum. Now, what do we have in solution B? Electrode Y is in solution B. Well, solution B also has manganate and manganese ions, and that means only ions in solution, no solids, then the electrode has to be a platinum electrode. A student suggested that for standard conditions, solution A should be made by mixing equal volumes of 1 mole per decimeter cubed iron 2 sulfate and 1 mole per decimeter cubed of iron 3 sulfate solution. Remember that we need equal volumes, 1 mole per decimeter cubed of each iron, but the iron 2 sulfate, each mole of iron 2 sulfate gives 1 mole of iron 2 ions, while each mole of iron 3 sulfate gives 2 moles of iron 3. So if the student mixes 1 mole per decimeter cubed of each one, equal volumes, this is wrong. The mixture is not suitable for measuring the standard electrode potential. State how this mixture should be changed. Remember, if 1 mole of the iron 2 sulfate gives 1 mole of iron 2 ions, while the other one gives 2 moles, then we should not start with equal volumes of equal concentrations. We should actually have 2 mole. Remember, we're diluting it. We're adding equal volumes. So if I'm starting with 1 mole per decimeter cubed of iron 2 sulfate, this is actually diluted when we add equal volumes. So what we should do actually, in order to get in the end 1 mole per decimeter cubed of each of the iron ions, I should use 2 mole per decimeter cubed of iron 2 sulfate and 1 mole per decimeter cubed of iron 3 sulfate. Then we have equal number of moles of the iron 3 plus and iron 2 plus, and when they are diluted, each of them were diluted by adding them together, then each of them would have a concentration of 1 mole per decimeter cube. Please be careful with respect to this. Then identify, okay, what were we talking about again? We were saying we want iron 2 plus to change to iron 3 plus. So we had a beaker that had iron 2 and iron 3. And we want to change manganate to manganese 2 plus. So the other beaker should contain which compounds? Identify the compounds that may be used to make solution B. So I want compounds of manganate and manganese 2 plus that are solutions. So usually the permanganate is usually potassium permanganate solution, and we need manganese ions that are soluble, that will form solution, not a precipitate. So we can use manganese 2 nitrate solution. A student suggested that the salt bridge could be made by soaking a strip of filter paper in barium nitrate. So he's using, instead of a U-tube with concentrate solution, he can connect them with a filter paper. That's okay. But he's soaking the filter paper in barium nitrate. So actually, the salt bridge now has barium nitrate solution. A reaction occurs when this salt bridge comes into contact with iron 2 sulfate. Remember, barium nitrate was tested for what? When we were doing ions, you should know that barium nitrate reacts with anything sulfate. It is tested for sulfate ions actually. So state what observation would be made. So if I have barium nitrate with something sulfate, what should we see? A white precipitate. Now write the ionic equation for the formation of the white precipitate. Of course, if I have barium ions, it reacts with the sulfate ions to give barium sulfate in the form of a white precipitate. So that is a solid. Include state symbols. Okay? Suggest a more suitable compound. So instead of using barium nitrate in the salt bridge, again, we said what should we use? We use something that is soluble and will not form a precipitate. So potassium nitrate, a saturated solution of potassium nitrate, would be a suitable compound in the salt bridge. Calculate E naught for the cell. So this was the reaction. that we were talking about. Use data in the data booklet. If you look at your data booklet, you will find this information. Iron 3 plus to iron 2 plus has an E cell of or reduction potential of 0.77. The manganate ions have a reduction potential of plus 1.51. So these are from the data booklet. And then I look at the equation. Do we want them as they are or should we invert them? Well, of course, the iron 2 plus, I want iron 2 plus to iron 3 plus. So that is the inversion of what I got from the data booklet, and that means I need to invert the sign. So now it's a minus 0.77. The manganate is as it is, plus 1.51. Add them up, the E cell is plus 0.74. Remember that the overall E cell is E oxidation plus E reduction. That's one way of doing it. Or you could say it is the subtraction of the two of them, but I prefer to write them like this. Question says, using the standard electrode potentials in the table, assess the thermodynamic feasibility of preparing manganate 6 by reacting manganate 7 and manganese 4 oxide in alkaline conditions. So we choose the relevant equations from the table. The manganate MnO4 minus to MnO4 2 minus, and the MnO4 2 minus I wanted to change from MnO2 to MnO4 2 minus. In this case, you're going to take the E cell of each one. Remember, we inverted that second equation, so we're going to invert the sign. The E cell here is minus 0.03 volts. So this is negative value. So the reaction is not feasible. But remember that this is in alkaline conditions. So first of all, the E cell is negative, reaction is not feasible. But because the negative value is very, very small, a slight increase will make it positive. And we could do this slight increase by adding more concentrated alkaline solution. So the value is very small, and the equilibrium may be shifted to increase the electrode potential of that second equation if I use concentrated alkali. So actually, overall, the cell becomes positive and the reaction becomes feasible. An electrochemical cell is this. What is the cell diagram? Remember, we will be required to write the cell diagram for an electrochemical cell. How do we write a cell diagram? Well, we start on the left with the oxidation part. So where is the oxidation? The oxidation is from iron solid to iron 2 plus. So I write that with the state symbols, and I put one line between the iron solid to iron 2 plus. So this is one half cell. And then I have a salt bridge, and the salt bridge is indicated by a double line that indicates the presence of a salt bridge. And then the other part, which is the reduction. So this is from SN2 plus aqueous to SN solid with a line between them. This is how we write the cell diagram for any reaction. The standard electrode potential for the iron 2 is minus 0.44 volts. The total E cell is plus 0.3. What is the standard electrode potential for the tin 2 plus electrode system? Remember, if we write this, then the E cell is the addition of oxidation plus reduction. And where he's giving me the overall E cell is 0.3 or plus 0.3. So what is the electrode potential? Now, when I calculate it, this is minus 0.14. So this is and this is a reduction potential or an oxidation potential. We are changing SN2 plus to SN. So this that we get from the equation is already reduction. If the equation was oxidation, I should have inverted the sign. So already in the equation, what we're calculating is the E for SN2 plus going to SN solid. This is reduction, so that is my reduction. Then this question says some standard electrode potentials are shown. Which of these ions is most likely to catalyze the reaction between S2OA2 minus and the iodide ion? Remember that we want something that would react with them so that it catalyzes them and then it is regenerated. So we cannot use chloride. The chloride is negative and all of the reactants are negative. They will all repel each other. I can use the Fe2 plus, and this is actually what we use as a catalyst for this kind of reaction. This is a homogeneous catalyst in which the catalyst is in the same phase as the reactants. Now we cannot use the copper 2 plus and the copper plus. It is above the iodide. It cannot oxidize the iodide to iodine. Okay, so we're going to stop here and then we will continue the rest of the questions in the next video. Please follow with us as we go along. Thank you for listening.